Shift your gaze to the stars for a moment. What you're seeing isn't just light, it's history. Those twinkling points left their sources years, centuries, even millennia ago. Now think about Star Trek's Enterprise zipping past them at warp speed. The universe's strict speed limit, light's 300,000 kilometers per second, seems unbreakable. Yet here we are, daring to ask, could we outpace light itself, not by bending the rules but by bending space? Enter the warp drive, a concept ripped from sci-fi pages and dropped onto physicists' chalkboards. It's not magic, it's math, and today we're unraveling how this theoretical engine might rewrite the boundaries of human exploration. Hold tight, this journey stretches beyond Einstein's universe. Einstein's theory of relativity isn't just a cornerstone of modern physics, it's the universe's rulebook. Picture this, the speed of light isn't merely fast, it's the ultimate speed limit, hardwired into the fabric of space and time. According to relativity, as an object approaches light speed, its mass balloons infinitely, demanding infinite energy to push it further. That's why breaking this barrier isn't just difficult, it's fundamentally impossible under our current understanding of physics. This cosmic speed limit puts interstellar travel in perspective. The closest star to Earth, Proxima Centauri, sits 4.2 light-years away. Even with our fastest spacecraft, reaching it would take tens of thousands of years, far beyond a human lifetime. The dream of exploring distant worlds or making contact with other civilizations slams into this harsh reality. But what if Einstein's rules aren't the final word? Some physicists argue relativity doesn't forbid bending space itself, creating shortcuts where speed limits no longer apply. The warp drive concept plays by these rules, not breaking them but sidestepping them entirely. Before we explore that tantalizing possibility, let's first grasp why light speed remains an unshakable boundary and what that means for our place in the cosmos. Here's the next segment. The idea of a warp drive sounds like pure science fiction, and in many ways it is. Think of Star Trek's iconic starships gliding through the cosmos, engines humming as they leap across the galaxy in days instead of centuries. But here's the twist, the concept isn't just fantasy. It's grounded in real physics, just taken to its most extreme possibilities. Unlike traditional rockets that push against something burning fuel to propel forward, a warp drive doesn't move through space the usual way. Instead, it manipulates space itself, compressing it in front of the ship and expanding it behind. Picture standing on a moving walkway. You're not striding faster, but the ground beneath you shifts, carrying you forward effortlessly. That's the core idea. By warping spacetime, the ship rides a bubble of distorted geometry, never actually accelerating beyond light speed locally. This isn't some wild cheat code, it's a loophole in Einstein's rules. Relativity says nothing can outpace light through space, but it says nothing about stretching space itself. The catch, the energy required would be staggering. Some estimates suggest needing the mass energy of an entire planet just to power a small craft. Yet the math checks out, which is why scientists like Miguel Alcubierre took the idea seriously, transforming sci-fi speculation into a legitimate theoretical framework. So while we're light years away from building a functioning warp drive, the fact that it's even a topic of scientific debate is thrilling. It means humanity's greatest adventures might not be limited by speed, but by our ability to bend the universe to our will. In the mid-90s, a Mexican theoretical physicist named Miguel Alcubierre did something extraordinary. He took warp drive from the realm of Star Trek and gave it a seat at the table of real science. His groundbreaking 1994 paper didn't just speculate. It laid out a mathematically sound framework for faster-than-light travel that, on paper at least, obeyed Einstein's laws. Here's how Alcubierre's vision works. Instead of trying to push a spacecraft through space at impossible speeds, his drive manipulates spacetime itself. Imagine space as a stretchy fabric. In front of the ship, this fabric contracts, pulling distant points closer together. Behind the ship, it expands, pushing space outward. The craft sits inside a stable bubble, what physicists now call a warp bubble, surfing this wave of distorted spacetime without actually moving through space the conventional way. Locally, inside the bubble, the ship never breaks light speed, but to an outside observer, it appears to race faster than light by riding the folds of the universe. Alcubierre's genius was showing that, mathematically, this doesn't violate relativity. Space can stretch and squash without limit because, unlike objects within space, spacetime itself isn't bound by the speed of light. But there's a catch. Creating this warp bubble requires something exotic: negative energy, a theoretical form of matter with repulsive gravity. We've glimpsed hints of such energy in quantum experiments, but harnessing it at the scale needed for a warp drive, that's still beyond our reach. Yet Alcubierre's paper ignited serious scientific discussion. Suddenly, warp drives weren't just for TV. They were a challenge for physicists to dissect, refine, or even debunk. His work proved that the universe might still hold tricks we haven't uncovered, loopholes that could one day turn humanity into an interstellar species. The question is no longer, is it possible, but how could we make it possible? And that shift alone changes everything. To grasp how a warp drive might actually work, let's borrow a tool physicists love, the rubber sheet analogy. Picture spacetime as a stretchy fabric, like a trampoline stretched taut. Planets and stars create dimples in this fabric, their gravity warping the surface. The heavier the object, the deeper the dent. Now imagine placing a bowling ball in the center that's a star bending spacetime around it. Light passing nearby doesn't move in a straight line. It follows the curve, like a marble rolling around the edge of that dip. This same principle applies to warp drive theory, but with an ingenious twist. Instead of just letting gravity pull space inward, what if we could control that bending? Envision pressing down on the rubber sheet ahead of a tiny spaceship while pulling it upward behind. The area in front contracts, bringing distant points closer while the space behind expands, pushing the fabric outward. The ship itself rests in a flat pocket between these distortions, untouched by acceleration forces. Here's where the magic happens. Inside this warp bubble, spacetime remains calm. Passengers wouldn't feel the crushing G-forces of traditional acceleration. Meanwhile, the fabric of space itself does the heavy lifting, carrying the craft forward like a surfer riding a wave. The ship never moves through space faster than light. It's space that moves around the ship, rewriting the rules of the game. Visualizing this as a rubber sheet makes the physics less abstract, but the reality is far more complex. Creating such a bubble requires precise, unimaginable energy, something akin to folding the universe like origami while ensuring the paper doesn't tear. Yet the analogy holds power. It transforms warp drive from a bewildering equations on a chalkboard into something we can almost feel. And that's the first step toward turning science fiction into science fact. The secret sauce behind warp drive physics isn't rocket fuel, it's something far stranger. To bend spacetime into a bubble, you'd need a type of energy that doesn't just push against gravity but flips it upside down. Enter negative energy, a theoretical form of matter with repulsive gravity. Think of it as cosmic anti-glue. While normal matter pulls space inward, negative energy would push it outward, creating the expansion behind a warp bubble that lets the ship surf forward. Here's why this bends more than just space, it bends our understanding of physics. In Einstein's universe, energy warps spacetime, but it usually does so predictably. Negative energy, it defies the textbook rules, generating gravity that repels rather than attracts. Picture trying to build a tunnel by pressing outward on the walls instead of digging. It's counterintuitive, but according to quantum mechanics, not impossible. Tiny glimpses of this effect already exist. The Casimir effect, where two metal plates in a vacuum somehow attract each other, hints at negative energy densities at microscopic scales. But scaling this up to warp drive levels is like comparing a candle to a supernova. Current estimates suggest you'd need a chunk of exotic matter with the mass energy of Jupiter just to warp space enough for a modest spacecraft. And that's before tackling the instability problems. Some models show warp bubbles collapsing into violent shockwaves or requiring impossible precision to sustain. Yet the fact that negative energy isn't outright forbidden by physics keeps the dream alive. It's a reminder that the universe still holds mysteries we've barely scratched. Until we unlock those secrets or find an alternative, warp travel remains suspended between science and imagination, a theory waiting for its breakthrough. Now let's turn our attention to the quantum realm, where the impossible might just be hiding in plain sight. In the world of the very small, particles flicker in and out of existence, defying our everyday expectations. One such phenomenon, the Casimir effect, offers a tantalizing glimpse at how negative energy might actually exist in nature. Picture two thin metal plates placed incredibly close together in a vacuum, so near they're almost touching. According to quantum theory, even empty space isn't truly empty. It crackles with virtual particles popping in and out of existence. Normally, these particles push equally in all directions, but when you bring these plates close enough, something strange happens. The space between the plates restricts which virtual particles can appear, while the space outside remains unaffected. The result, a minuscule but measurable force pushing the plates together. This might sound like an obscure physics curiosity, but here's the kicker. The math suggests this effect creates a region of negative energy density. For a split second, in that microscopic gap, space itself behaves in a way that aligns with the exotic matter a warp drive would require. It's not enough to power a starship, of course. We're talking about forces on the scale of billionths of a Newton. But it's proof that nature allows energy to behave in ways we once thought impossible. Scientists are now running experiments to amplify or harness this effect, probing whether we might one day scale it up. Projects like NASA Eagleworks lab and advanced quantum vacuum research are pushing the boundaries, searching for ways to stabilize and manipulate these energy fluctuations. The Casimir effect is more than a lab oddity. It's a doorway into a deeper understanding of spacetime's hidden mechanics. And if we can unlock its secrets, we might just find the missing puzzle piece for bending the universe to our will. Let's talk numbers, because the energy needed to power a warp drive isn't just high, it's unimaginable. Alcubierre's original calculations suggested something jaw-dropping. To create a warp bubble around a modest spacecraft, you'd need energy equivalent to converting Jupiter itself entirely into fuel. That's not just impractical, it's physically absurd with today's technology. But here's where the story gets interesting. Later, physicists re-examined Alcubierre's math and found ways to slash those requirements. By tweaking the warp bubble's shape, making it thinner, or adjusting its geometry, they reduced the energy needs from a planetary scale to something closer to a large asteroid's mass. Still enormous, but now in the realm of theoretical plausibility. Some optimists even suggest that with a warp bubble just a few meters wide, the energy could drop to the mass of the Voyager 1 probe, about 700 kilograms. Yet even that small number hides a catch. This energy couldn't be ordinary matter. It'd need to be exotic, with negative energy properties, and harvesting or creating that much exotic matter remains beyond our reach. Even if we could, stabilizing the bubble introduces new hurdles, like preventing destructive quantum instabilities or steering the ship without tearing spacetime apart. The takeaway: warp drive energy demands have shrunk from impossible to maybe one day, but one day hinges on breakthroughs we can't yet predict. It's a reminder that while physics bends for no one, our understanding of it never stops evolving. And that's where the real hope lies. Flying inside a warp bubble might sound like smooth sailing through the stars, but the reality could be far more treacherous. Picture a spacecraft encased in its own little pocket of spacetime while the universe bends violently around it. The passengers might feel nothing, but outside that protective bubble, forces powerful enough to shred matter lurk in every direction. Radiation poses one of the deadliest threats. As space compresses in front of the ship, any particles caught in that region would get whipped into ultra-high-energy projectiles. Without proper shielding, they'd blast through the hull like cosmic bullets. Then there's Hawking radiation, theoretical energy that could erupt along the edges of the warp bubble, frying electronics and crew alike. Early models suggested this radiation might grow so intense it would destabilize the bubble itself, collapsing the whole system in a catastrophic failure. But physicists aren't leaving these problems unanswered. One proposed fix, adjusting the bubble's geometry. Instead of a perfect sphere, a toroidal or donut-shaped warp field could deflect harmful radiation away from the ship. Others suggest layering the bubble with zones of varying spacetime curvature, creating a buffer against tidal forces that might otherwise stretch the ship like taffy. Even more intriguing is the idea of quantum shielding, borrowing principles from theoretical physics to create a barrier that deflects or absorbs harmful energy. Some models hint at using the same exotic matter fueling the warp drive to form a protective shell, turning the problem into its own solution. Of course, these are all ideas on paper. We're still decades, maybe centuries, from knowing if they'd hold up in reality. But that's the thrill of science. Each challenge invites a new wave of creativity. The dream isn't just to travel faster than light, but to do it without becoming stardust along the way. Here's the next segment. One of relativity's strangest consequences is how time bends along with space, what physicists call time dilation. At near light speeds, clocks tick slower for travelers than for those left behind. Imagine an astronaut returning to Earth after a high-speed journey only to find their twin has aged decades more. But warp drives promise something radical, sidestepping this cosmic quirk entirely. Here's why. Traditional near-light travel forces astronauts through extreme acceleration, subjecting them to relativity's full time-stretching effects. Warp travel flips the script. Since the ship isn't moving through space but riding a bubble of warped spacetime, local physics inside remains untouched. Passengers would experience time normally, no twin paradox, no biological whiplash to them. The trip might feel like weeks while centuries pass outside the bubble. But this raises a fascinating twist. While warp travelers avoid time dilation's personal toll, they'd still face a universe that aged without them. Arriving at Proxima Centauri after a 2-year journey might mean returning to an Earth 4.2 years older, not millennia, as with relativistic flight, but enough to reshape relationships, cultures, even civilizations. Warp drives wouldn't defy time, they'd negotiate it differently, trading one set of consequences for another. The takeaway: warp travel doesn't erase time's arrow, it just gives us a stranger, more navigable relationship with it. And that might be the ultimate trade-off, the freedom to roam the stars without losing ourselves to time's relentless flow. Now let's confront one of warp drive's most mind-bending consequences, time's delicate domino effect. Imagine accelerating past light speed, not just through space, but through cause and effect itself. Traditional faster-than-light travel isn't just about speed. It risks unraveling the very sequence of events, creating paradoxes where an effect could precede its cause. Picture the infamous grandfather paradox. Travel back in time, prevent your grandparents from meeting, and suddenly you couldn't exist to make the trip in the first place. Here's where warp drives complicate things. In Einstein's universe, causality, the unbreakable law that causes must come before effects, is stitched into spacetime's fabric. Standard FTL schemes shatter this, but warp bubbles might sidestep the issue or make it worse. Some physicists argue that by riding bent spacetime, a warp ship never technically exceeds light speed locally, preserving causality inside the bubble. Others counter that to an outside observer, the ship still arrives before it departs, effectively time traveling. The debate hinges on subtle physics. If a warp bubble forms a closed time-like curve, a loophole where an object's path through spacetime loops back on itself, it could allow paradoxes. Yet recent models suggest solutions. Perhaps warp fields naturally destabilize when paradoxes arise, or quantum mechanics intervenes to prevent contradictions. Either way, the stakes couldn't be higher. If warp drives permit causality violations, every trip could rewrite history. Until we solve this riddle, FTL travel remains as much a philosophical challenge as a technical one, forcing us to ask not just can we bend spacetime, but should we? At NASA Johnson Space Center, tucked away in a lab marked Eagleworks, a team led by physicist Harold "Sonny" White has been chasing what most consider impossible: measuring the fingerprints of a warp field. Their experiments sound like something from a sci-fi novel: lasers firing across an interferometer, hunting for microscopic ripples in spacetime itself. The centerpiece of their work is a device called the White-Jude Warp Field Interferometer. It works by splitting a laser beam into two paths, one through empty space, the other through a region where electric fields are manipulated in ways that might, theoretically, create a tiny warp bubble effect. If spacetime distorts even slightly, the laser beams would recombine out of sync, revealing a telltale interference pattern. In 2013, White's team reported something startling: anomalous readings that hinted at minuscule spacetime distortions. The scientific community reacted with equal parts intrigue and skepticism. Critics pointed out potential experimental errors, while supporters argued that even inconclusive results push the boundaries of known physics. What makes Eagleworks compelling isn't just the technology, it's the philosophy. White's approach treats warp drive not as fantasy but as an engineering challenge. His team has proposed refinements, like using ring-shaped capacitors to stabilize warp fields, and even conceptualized a spacecraft design called the IXS Enterprise, a nod to Star Trek with a foundation in real equations. Of course, we're not talking about folding space tomorrow. The energy demands remain astronomical, and the effects measured so far are vanishingly small. But Eagleworks represents something vital: the willingness to test ideas at the edge of plausibility. In science, the line between breakthrough and blind alley isn't always clear until someone walks it. And right now, in a quiet Houston lab, that walk has begun. Warp drives often steal the spotlight in faster-than-light discussions, but they're not the only cosmic shortcut on the table. Wormholes, those elusive tunnels through spacetime, offer an equally tantalizing path to the stars. The real question isn't just which one feels more sci-fi, but which one physics might actually permit. Imagine space as a vast sheet of paper. A warp drive folds that paper, bringing distant points closer by bending the fabric itself. A wormhole, though, it's like poking a pencil through the sheet, creating a literal tunnel from one side to the other. Both ideas dodge the light speed limit, but they play by wildly different rules. Wormholes rely on Einstein's equations too, but they demand something even more exotic: stable, traversable bridges lined with negative energy to keep them from collapsing instantly. Energy requirements tell a revealing story. While warp drives need planet-scale power to sustain their bubble, wormholes might, in theory, require less if they're naturally occurring cosmic structures. The catch: no one's ever found a natural wormhole, and building one from scratch would involve manipulating spacetime with precision we can't yet fathom. Then there's the safety factor. Warp bubbles risk deadly radiation and instability, but wormholes could be far worse. Traversing one might expose travelers to tidal forces strong enough to spaghettify matter, or worse, collapse mid-journey, stranding ships in oblivion. Some models even suggest wormholes could link not just space but time, opening Pandora's box of paradoxes. Yet wormholes have one edge: they're already embedded in relativity's math. Einstein and Rosen proposed them as bridges between black holes back in 1935. Warp drives, by contrast, are a later addition, meaning wormholes have had decades more scrutiny. So which wins? Neither yet. Both concepts stretch our understanding of physics to its limits. Warp drives offer controlled, localized travel, while wormholes promise instant jumps across the cosmos. But until we uncover the secrets of negative energy or stumble upon a stable wormhole in the wild, these remain two sides of the same speculative coin. The answer might not be choosing one over the other, but learning which secrets the universe is willing to give up first. While warp bubbles dominate the conversation about faster-than-light travel, there's another cosmic shortcut hiding in the equations, one that twists space-time into tunnels rather than waves. Meet the Krasnikov tube, a concept so underrated it feels like physics' best-kept secret. Proposed by Russian physicist Sergei Krasnikov in the 1990s, this model doesn't rely on surfing a distortion bubble. It builds a permanent highway through the stars. Here's how it works. Imagine a spacecraft traveling to a distant star at near light speed. As it moves, it leaves behind a trail of pre-warped spacetime, a tunnel where the return trip would take far less time than the outbound journey. Unlike the Alcubierre drive, which compresses space in front of and expands it behind the ship, a Krasnikov tube is more like a subway line through the universe. Once constructed, anyone could use it to zip back and forth without needing exotic matter for each trip. The trade-offs for starters, building the tube would require the same staggering energy as a warp drive just upfront, like laying railroad tracks across light years. And while Alcubierre's bubble lets you change course mid-journey, Krasnikov's tunnels are fixed routes. Miss your exit, and you're stuck on the cosmic freeway until the next off-ramp. There's also the causality problem. Just like warp drives, these tubes could potentially create time loops where messages or travelers arrive before they depart. Yet the Krasnikov tube offers something revolutionary: scalability. Once established, these pathways could become interstellar infrastructure. Think of them as intergalactic canals open to any ship with the right coordinates. No need to haul Jupiter's worth of exotic matter for every voyage. That's why some physicists quietly argue it might be the more practical long-term solution, even if it lacks the flashy appeal of warp bubbles. So which idea wins? Neither yet. Warp drives promise spontaneity. Krasnikov tubes offer reliability. One bends space on demand, the other builds roads for eternity. But both whisper the same tantalizing truth. The universe's rulebook might still have pages we haven't turned, and that's where the real adventure begins. Quantum mechanics throws a curveball at warp drive dreams. What works on paper often crumbles under quantum scrutiny. Take exotic matter, the hypothetical fuel for bending spacetime. The math says we need it, but nature seems to resist. Unlike regular matter, exotic particles would require negative mass, meaning they'd repel rather than attract. Theoretically, they could exist as quantum fluctuations, tiny, fleeting anomalies in the vacuum of space, but scaling these up to warp drive quantities. That's like trying to build a skyscraper out of soap bubbles. Then there's Hawking radiation, a phenomenon usually linked to black holes. Inside a warp bubble, similar physics might unfold. The edges of the distorted spacetime could seethe with quantum particles' energy so intense it risks frying the ship or destabilizing the bubble itself. Some models suggest this radiation could grow exponentially, turning the warp field into a death trap of high-energy chaos. But quantum weirdness isn't all bad news. The same laws that create these hurdles might also offer solutions. Quantum vacuum propulsion, for instance, explores harnessing the energy of empty space itself, akin to sailing a ship by catching the wind between stars. And while exotic matter remains elusive, advances in metamaterials, engineered substances with unnatural properties, hint that we might one day mimic its effects in a lab. The takeaway: quantum physics doesn't just stack obstacles, it reshapes the playing field. Every time we hit a wall, it forces us to imagine a door, and behind that door could be the key to folding the universe itself. Bending spacetime sounds thrilling until you realize it might come with cosmic side effects like accidentally birthing a black hole. This isn't just theoretical hand-wringing, it's a genuine concern rooted in Einstein's own equations. When you warp space enough to outrun light, could you also twist it into a singularity? Some physicists warn the answer might be yes. The worry hinges on something called cosmic censorship, an idea proposed by Roger Penrose suggesting the universe has safeguards to prevent naked singularities or black holes without event horizons from forming. These would be catastrophic, exposing their infinite density to the rest of reality. Warp drives, by distorting spacetime so severely, could poke holes in this cosmic firewall. Picture compressing space in front of a ship like squeezing a balloon. Push too hard, and the fabric of spacetime might not just bend, it could snap. Mathematical models show that under extreme curvature, the warp bubble's edges could collapse into a singularity, trapping the ship inside its own artificial black hole. Even worse, such an event might release bursts of Hawking radiation, frying the ship and anything nearby. But here's the counterargument: warp fields might self-regulate. Just as water resists being torn apart by surface tension, spacetime could have quantum safeguards that prevent catastrophic collapse. Some simulations suggest that instabilities would dissipate the bubble before a singularity forms, like a wave smoothing out before it crashes. The debate isn't settled, and that's the point. Warp drive research isn't just about building engines, it's about probing the limits of the universe's rulebook. Every equation whispers a warning: manipulate space at your peril, but also teases a possibility that we might one day navigate these dangers like cosmic tightrope walkers. The silence of the cosmos is deafening. If warp drives are theoretically possible, why haven't we encountered a single civilization zipping across the galaxy? This haunting question lies at the heart of the Fermi paradox, the glaring contradiction between the high probability of alien life and our complete lack of evidence for it. Warp technology might hold a clue to this cosmic mystery. One unsettling possibility is that advanced civilizations avoid warp travel entirely, not because they can't master it, but because they've discovered something terrifying in the process. Imagine a species stumbling upon the dangers we've discussed: black hole formation, causality violations, or spacetime ripples that destabilize entire star systems. What if the energy required for warp drives inevitably leads to catastrophic feedback loops? A single miscalculation could tear apart the fabric of local spacetime, turning a starship into a doomsday device. Then there's the darker alternative. Maybe they are out there, warping through the galaxy, but we're looking for the wrong signs. Traditional searches for extraterrestrials focus on radio signals or megastructures, but a warp-capable civilization might leave subtler traces. Ripples in cosmic background radiation, anomalous gravitational waves, or even brief distortions in starlight could be their signatures. We might already have detected these clues without realizing their significance, like ancient astronomers mistaking supernova for celestial omens. But here's the most humbling thought of all: what if warp travel is possible but universally pointless? The energy costs might be so prohibitive that even the most advanced civilizations prioritize slower, safer methods. Generation ships or cryogenic hibernation could be more practical than gambling with spacetime. Or perhaps intelligent life inevitably evolves beyond physical exploration, preferring virtual realities or quantum communication over star hopping. The Fermi paradox isn't just a question about aliens, it's a mirror. Our fascination with warp drives reflects our own hunger to explore, but it also forces us to confront the unnerving idea that the universe might hide roadblocks we can't yet see. Until we crack those codes, the stars remain silent, leaving us to wonder if the real barrier isn't speed, but survival itself. Picture Earth's economy today: ships crossing oceans, planes stitching continents together, all bound by the speed of cargo and the patience of trade routes. Now erase those limits. With warp technology, a mining operation in the asteroid belt could deliver rare metals to Mars within hours, not months. A colony around Proxima Centauri might export biotechnology to Earth before their research papers even finish peer review. The concept of globalization would shatter, replaced by something far grander: interstellar capitalism. The first ripple: resource abundance. Suddenly, water isn't just an Earth commodity, it's harvested from Enceladus geysers and Kuiper belt ice. Rare minerals aren't dug from contested terrestrial mines but collected from metallic asteroids, collapsing scarcity overnight. Economies wouldn't just grow, they'd explode, untethered from planetary boundaries. But abundance brings chaos. Traditional industries, oil, precious metals, even agriculture, could collapse under the weight of cosmic supply chains. Nations reliant on resource exports might find their wealth evaporating as asteroids become the new oil fields. Then there's the labor question. Near-instant travel redefines work itself. A surgeon could operate on patients across 3 star systems before lunch. Engineers might commute to orbital megastructures light years away, returning home each night. This isn't just flexible scheduling, it's the end of geography as a constraint on human potential. Yet lurking beneath is a darker asymmetry. Those controlling warp-capable ships would wield disproportionate power, creating a new class divide between those who hop stars and those stuck planetside. Cultural exchange would accelerate beyond prediction. Art, music, and ideas wouldn't trickle between worlds, they'd flood. Imagine a fashion trend born on a tidally locked exoplanet going viral on Earth within days, or alien culinary techniques revolutionizing kitchens galaxy-wide. But with this hyperconnectivity comes cultural homogenization risk, the galactic equivalent of every city having the same coffee chain. Perhaps most radical is the timescale shift. Traditional economics relies on interest, investment, and growth measured in years. With warp trade, compound interest could span star systems, and corporate empires might rise or fall within weeks. Stock markets would pulse with real-time data from 1,000 worlds, demanding AI traders faster than any human. The very concept of long-term would warp alongside spacetime itself. This isn't just about faster ships, it's about rewriting the rules of civilization. From post-scarcity utopias to corporate dystopias spanning light years, warp-driven trade wouldn't merely change economies. It would force us to reinvent what value even means in a universe where distance no longer dictates price. The question isn't whether we're ready for such a revolution, it's whether we can imagine it before it arrives. Humanity has spent centuries wondering if we're alone in the cosmos, but what if we're the first to crack warp travel? Suddenly, the tables turn. We become the advanced civilization arriving unannounced on someone else's galactic doorstep. That's not just a sci-fi scenario, it's a looming ethical dilemma. Right now, organizations like METI, messaging extraterrestrial intelligence, debate whether broadcasting our existence to the stars is wise. But warp capability forces a sharper question. When we can knock in person, what rules guide that first handshake? History offers grim warnings. Earth's own past is littered with first contacts gone wrong, cultures colliding with catastrophic misunderstandings. Now scale that to interstellar diplomacy. Imagine arriving at a planet where language isn't just foreign but non-vocal, or where concepts like individual rights or technology don't exist. Even with benevolent intentions, our mere presence could disrupt ecosystems, topple governments, or inadvertently introduce cosmic germs. The prime directive from Star Trek suddenly feels less like TV fiction and more like a survival manual. Current protocols are woefully unprepared. The Outer Space Treaty of 1967 forbids claiming celestial bodies but says nothing about greeting their inhabitants. SETI post-detection guidelines focus on verifying signals, not navigating face-to-face encounters. Some scientists argue for a galactic do-no-harm principle, sending passive probes first, studying civilizations from a distance before revealing ourselves. Others, like METI proponents, advocate bold transparency, announcing our arrival openly to avoid appearing covert or hostile. Yet warp tech adds another layer, the sheer speed of interaction. Radio signals take years to cross the void, allowing time for deliberation. But a warp-capable ship could go from discovery to landing in days. That urgency demands real-time decision-making. Do we share our technology? Offer medical aid, intervene in conflicts. Every choice could echo across millennia. Perhaps the most sobering truth is this: warp travel doesn't just expand our reach, it forces us to grow up as a species. Before we step onto alien soil, we'll need something far rarer than exotic matter, a unified vision of who we are and what we represent in the cosmic dark. The stars won't judge us by our engines, but by our wisdom, and that's the one technology no equation can guarantee. Imagine a world where warp technology exists, but only a handful of nations or corporations control it. The power to bend spacetime wouldn't just revolutionize travel, it would rewrite global power structures overnight. Who decides who gets access? Do we treat warp drives like nuclear weapons restricted to superpowers, or like the internet, an open frontier? The ethical dilemmas here aren't hypothetical. They're inevitabilities we'd face the moment this tech becomes real. Take resource allocation first. The energy demands alone could spark conflicts on an unprecedented scale. If exotic matter is scarce, do we prioritize scientific missions, military applications, or commercial ventures? Picture a future where private companies monopolize warp lanes, charging exorbitant fees for passage while entire nations are locked out of the stars. The risk isn't just inequality, it's a new era of interstellar feudalism where the cosmos becomes a playground for the ultra-wealthy. Then there's the geopolitical nightmare. Historically, breakthroughs in transportation from steamships to spaceflight have reshaped empires. Warp tech could dwarf these shifts, creating a rush to claim not just territories but entire star systems. Would we repeat colonialism's darkest chapters, exploiting alien worlds for resources? Or could we establish something like a United Nations for interstellar law, ensuring fair access and protection for undiscovered civilizations? But the most haunting question isn't about control, it's about responsibility. Warp travel doesn't just transport people, it carries cultural biases, ecological footprints, and unintended consequences. A single misstep, introducing invasive species to pristine worlds or disrupting fragile alien societies, could echo across millennia. We'd need more than regulations. We'd need a fundamental shift in how humanity views its role in the cosmos. The irony, the hardest part of warp technology might not be the physics but proving we're mature enough to wield it. Before we engineer the engines, we'd need to engineer fairness, foresight, and humility into the very systems that let us reach the stars. Because without those, we wouldn't be explorers, we'd just be the next cosmic bullies. Long before physicists put pen to paper, science fiction was already bending the cosmos to its will. Star Trek's USS Enterprise didn't just popularize warp drives, it gave us an entire visual language for faster-than-light travel. That iconic warp effect, with stars stretching into streaks as the ship lurches forward, wasn't just dramatic flair. It was a stroke of genius, capturing the essence of space-time distortion years before Alcubierre's equations made it plausible. But Trek's vision was just the beginning. Across decades of media, warp technology has mirrored our evolving understanding of physics and our wildest fantasies. The original Star Trek treated warp like a cosmic highway with clean, controlled jumps. Later series like The Next Generation introduced warp factors, a pseudo-scientific scale that hinted at exponential energy demands, something eerily close to real-world calculations. By contrast, Battlestar Galactica stripped away the glamour, presenting faster than light as a harrowing, fuel-guzzling gamble that left ships vomiting radiation. Then came the game changers. Interstellar's portrayal of a wormhole, a cousin to warp theory, grounded its spectacle in real science, with Kip Thorne ensuring the visuals matched relativity's equations. The result, a black hole's lensing effect so accurate it spawned new astrophysics papers. On the flip side, franchises like Star Wars treat hyperdrives like magic, skipping the science for the sake of adventure, and that's okay. These aren't flaws, they're choices reflecting how fiction bends science to serve story. Even comedy gets in on the act. The Hitchhiker's Guide to the Galaxy's Infinite Improbability Drive mocks the absurdity of FTL travel while somehow feeling less ridiculous than our real-world need for negative energy. Meanwhile, indie films like Prospect show warp as a grimy industrial tool, no glowing nacelles, just clunky machinery that might fail mid-jump. What's fascinating isn't just how these depictions differ, but what they share, a human desire to conquer distance. Whether it's Trek's optimism or Event Horizon's horror, each story asks the same question science does, just with more explosions. They remind us that warp drives aren't just about physics, they're about longing. The longing to explore, to connect, or sometimes just to get home. There's something primal in the way warp drives ignite our imagination, a hunger woven into humanity's DNA. For millennia, we've stared at the night sky and dreamed of crossing impossible distances. Ancient Polynesians navigated oceans by stars, medieval scholars sketched flying machines, and now we fantasize about folding spacetime itself. This isn't just about speed, it's the latest chapter in an age-old story, the refusal to be bound. Think of the myths that shaped us: Icarus with his wax wings, the Norse Bifrost Bridge linking worlds, even the Star Wars hyperdrive. Each reflects the same yearning to shatter barriers. Warp technology taps into that mythic vein, offering a tantalizing, what if that feels almost archetypal. It's not merely a propulsion system, it's a metaphor for liberation dressed in the language of physics. But there's more to it than poetry. The frontier mentality still pulses in our culture. The same drive that pushed explorers to sail beyond mapped edges now fuels our obsession with interstellar travel. Warp drives represent the ultimate frontier, not just new lands but entirely new worlds. They promise a universe where humanity isn't confined to a pale blue dot, but becomes a multi-planet, even multi-star species. And then there's the sheer audacity of it. In an era where technology often feels incremental, faster phones, sleeker apps, warp theory dares to envision a leap so radical it redefines what's possible. It's the antidote to existential claustrophobia, a reminder that the cosmos might still hold surprises. Whether through science or story, that idea resonates because it speaks to our deepest fear: being stuck. Stuck on Earth, stuck in time, stuck by the limits of our biology. Yet for all its grandeur, the appeal is also deeply personal. Who hasn't wished to outrun their own light, to leave behind regrets, revisit lost moments, or simply escape gravity's tug? Warp drives crystallize that fantasy into equations, offering hope that the universe might yet concede a loophole. They're not just engines, they're emancipation in hypothetical form. And that's why, whether in labs or movie theaters, we can't stop reaching for them. While warp drives remain a distant dream, humanity isn't waiting idly to touch the stars. Enter Breakthrough Starshot, a bold, today's technology approach to interstellar travel that could pave the way for tomorrow's warp breakthroughs. Picture this: ultra-light probes, no larger than a smartphone, equipped with gossamer thin light sails. Instead of bulky rockets, these tiny spacecraft would ride beams of focused laser light, accelerating to 20% the speed of light within minutes. At that pace, they'd reach Proxima Centauri in just 20 years, a blink compared to conventional missions. What makes Starshot so revolutionary isn't just the speed, it's the philosophy. By thinking small, scientists sidestep the energy nightmares of warp drives. No exotic matter, no Jupiter-sized fuel requirements, just precision optics and the relentless push of photons. Yet the challenges are staggering. These probes must survive decades of deep space radiation, navigate without onboard propulsion, and somehow transmit data back across 4 light years. Even the laser array needed to propel them would dwarf any infrastructure we've ever built. But here's where Starshot whispers lessons for warp research. Mastering laser propulsion could refine the energy-focusing techniques needed to manipulate spacetime. Learning to shield microscale probes might inform warp bubble stabilization. And the sheer act of coordinating interstellar missions trains us to think in cosmic terms, breaking free of earthbound engineering habits. Critics argue Starshot distracts from more ambitious concepts, but they miss the point. Every leap begins with a lean. The Wright brothers didn't start with jet engines, they built gliders. Similarly, Starshot's humble probes could be the first domino in a chain reaction of discovery, proving that even modest steps forward illuminate the path to the impossible. After all, before you fold space, you must first learn to push against it. Running warp drive experiments in a lab might sound impossible, but what if we could simulate them down to the quantum level? That's exactly where supercomputers step in, acting as digital laboratories where physicists can tweak warp geometries, adjust energy distributions, and even spot catastrophic instabilities, all before bending a single atom in the real world. Modern simulations don't just recreate warp bubbles, they stress test them. Take NASA collaborations with institutions like Oak Ridge National Laboratory, where teams feed Einstein's equations into some of the planet's most powerful supercomputers. These machines crunch numbers at speeds unfathomable just decades ago, modeling how spacetime would curve around a hypothetical ship. One simulation might reveal that a particular bubble shape funnels deadly radiation toward the cockpit, while another could show how tweaking the negative energy density prevents a warp field from collapsing into a black hole. The beauty of these digital experiments, they let researchers play what if with the universe's rulebook. Want to see what happens if a warp bubble grazes a neutron star's gravity? Simulate it, curious whether multiple bubbles could create a stable tunnel. Run the numbers. Supercomputers handle scenarios too risky or expensive to attempt physically, like probing the moment a warp field brushes against the speed of light, where relativity and quantum mechanics clash violently. Yet even silicon brains have limits. Some quantum effects remain devilishly hard to model, and approximations can mask pitfalls. That's why teams like those at the University of Valencia cross-check simulations with analytical math, searching for gaps where digital shortcuts might hide real-world dangers. What's emerging is a feedback loop between theory and simulation, each refining the other. Every iteration inches us closer to knowing whether warp drives are a future certainty or a beautiful dead end. For now, these virtual warp bubbles are our best map into the unknown, proving that sometimes the most powerful engine for discovery isn't a starship, but a well-programmed machine. Alcubierre's warp drive was just the beginning. Like Newton's apple, it sparked a revolution we're still navigating. The past decade has seen physicists re-engineer his original concept, chipping away at obstacles once thought insurmountable. Take the energy problem. Newer models suggest we might not need a planet's worth of exotic matter after all. By flattening the warp bubble into a thinner, ring-shaped geometry, researchers like Alexei Bobrik and Gianni Martire slashed energy demands to something closer to a small moon's mass. Still astronomical, but no longer laughably impossible. Then there's the quantum leap, literally. Recent papers fuse warp theory with quantum field dynamics, revealing unexpected loopholes. One tantalizing proposal involves manipulating vacuum fluctuations, the same quantum froth that powers the Casimir effect. Instead of relying solely on exotic matter, this approach would borrow energy from spacetime itself, briefly stabilizing a warp bubble before it snaps back like a stretched rubber band. It's speculative, but it hints at a universe more flexible than we imagined. Even the stability hurdles are getting fresh scrutiny. Early models warned that warp bubbles might collapse into shock waves, but 2020, two simulations by University of Alabama physicists showed that certain configurations could self-correct, like a surfer adjusting their stance to ride a wave. Others explore layering multiple bubbles, think nested Russian dolls, to distribute stress and prevent catastrophic failures. But perhaps the most intriguing twist comes from unexpected corners. A 2024 paper in Classical and Quantum Gravity reimagined warp drives not as engines but as natural phenomena. If cosmic strings hypothetical spacetime defects from the Big Bang exist, they might naturally bend space in ways resembling Krasnikov tubes. Suddenly, warp travel isn't just about building technology, it's about learning to harness the universe's own shortcuts. These aren't just incremental tweaks, they're paradigm shifts. Each paper reframes the challenge, proving that Alcubierre's idea was a starting pistol, not a finish line. The equations keep whispering, the universe may yet yield a path to the stars if we're clever enough to listen. The universe isn't just expanding, it's accelerating, as if some unseen hand is stretching spacetime itself apart. Scientists call this mysterious force dark energy, and it makes up nearly 70% of the cosmos. But here's the twist. While physicists struggle to explain what dark energy is, warp drive researchers are asking a radically different question. Could we use it? Think about how dark energy behaves. Unlike gravity, which pulls matter together, dark energy pushes space outward, creating more distance between galaxies over time. That's eerily similar to the expansion half of a warp bubble, where spacetime stretches behind a hypothetical starship to propel it forward. The parallel is too striking to ignore. What if dark energy isn't just a cosmic curiosity, but a blueprint for manipulating spacetime? Not all researchers are convinced, of course. Dark energy's effects are subtle, spread thinly across the vast emptiness between galaxies. Concentrating that force into a controlled warp field would be like trying to bottle a hurricane, except we don't even know what the hurricane is made of. Some theorists argue that dark energy might not even be a form of matter or energy as we understand it, but a fundamental property of spacetime itself. If that's true, harnessing it could be like trying to grip water with your bare hands. Yet the tantalizing possibilities keep scientists digging. Could advanced civilizations, if they exist, have already cracked this connection? Some models suggest that regions of intense dark energy, like the voids between galactic superclusters, might naturally create spacetime distortions akin to warp bubbles. If so, studying these cosmic blank spots could be the key to reverse engineering a warp drive. Others speculate that dark energy might not power a warp engine directly, but serve as a cosmic signpost, pointing toward deeper physics that could make spacetime manipulation possible. One thing's certain, dark energy reminds us how little we know about the universe's inner workings. Every unexplained phenomenon is a locked door, and behind this one might lie not just answers about the cosmos' fate, but the tools to defy it. For now, the link between warp drives and dark energy remains a thrilling hypothesis, blending the edges of astrophysics and engineering. But in a universe where space itself is stretching faster than light, perhaps the real question isn't if we'll find a connection, but when. Crossing the vast emptiness between stars is one thing, but what about vaulting the unimaginable gulf between galaxies? The Andromeda Galaxy, our closest galactic neighbor, floats a staggering 2.5 million light-years away. Even at warp speeds that defy physics, reaching it would test the very limits of any theoretical drive. Start with the numbers. If a warp bubble could sustain a consistent speed of 100 times light speed, already a colossal leap beyond anything we've imagined, the trip to Andromeda would still take 25,000 years. That's longer than all recorded human history. Scale up to 1,000 times light speed, and you're still looking at a 2.5 millennium journey. The challenge isn't just speed, it's endurance. Could any warp field remain stable across such unfathomable distances? or would quantum fluctuations, cosmic radiation, or exotic matter decay erode the bubble over millennia? Then there's the energy problem. The Alcubierre drive's fuel needs already border on the absurd for interstellar hops, but intergalactic voyages demand exponential leaps. Some calculations suggest warping to Andromeda might require more energy than our galaxy contains. Even if exotic matter could be harvested efficiently, would there be enough in the observable universe to power such a voyage? But here's the tantalizing counterpoint. Warp technology might not need to shoulder the entire burden. If cosmic shortcuts like naturally occurring wormholes or Krasnikov tubes exist between galaxies, a hybrid approach could emerge: short bursts of warp travel between stable spacetime tunnels. Alternatively, a multi-generational warp ship sustaining a bubble for epochs might inch humanity closer to the idea of galactic pioneers, the real revelation. Andromeda isn't just a destination, it's a litmus test for whether physics permits civilizations to outlast their home galaxies. As Andromeda and the Milky Way slowly collide in 4 billion years, warp-capable species might thrive in the chaos, hopping between stars like cosmic nomads. Until then, the dream of touching another galaxy remains the ultimate yardstick, not just for our engines, but for our ambition. Gazing into the future of warp research feels less like reading a roadmap and more like deciphering a treasure map, full of tantalizing possibilities with no guaranteed path. Where could this wild frontier lead us in the coming decades? Let's follow the breadcrumbs left by today's top physicists and engineers. Near-term goals are surprisingly pragmatic. Over the next 5 to 10 years, labs like NASA Eagleworks aim to refine their interferometry experiments, hunting for microscopic spacetime distortions with ever greater precision. Think of it as tuning a cosmic radio. Each adjustment brings us closer to detecting the faintest whisper of a warp effect. Meanwhile, quantum physicists are racing to stabilize fleeting negative energy phenomena in controlled settings, much like early chemists isolating elements for the first time. Small steps but critical, because before we bend space, we must first learn to measure its pliability. By mid-century, the ambitions scale up dramatically. With advancements in metamaterials and quantum vacuum engineering, some researchers predict tabletop-scale warp bubble prototypes, not for propulsion yet, but as proof of concept. These wouldn't be starships, but rather space-time tuning forks that validate the math in the lab. Experts like Dr. Harold White suggest this phase could resemble the 1940s of nuclear research. We'd grasp the fundamentals but lack the infrastructure to go big. The real horizon-stretching predictions kick in post-2070. If exotic matter production becomes feasible, perhaps via scaled-up Casimir effect manipulation or breakthroughs in dark energy control, we might see the first meter-scale warp drives. Picture a modern particle accelerator, but designed to twist local spacetime geometry. Even then, interstellar travel remains distant. These early systems would more likely revolutionize satellite propulsion or enable rapid solar system hopping. Optimists in the field, including a vocal contingent at the Applied Physics Group, argue that a functioning Starship-capable warp drive could emerge by 2200, assuming sustained funding and no show-stopping physics barriers. Their models suggest a gradual upscaling, lab success to robotic probes, then crewed vessels. Pessimists counter that the energy hurdles may forever relegate warp drives to theoretical exercises, pushing humanity toward slower alternatives like generation ships or cryostasis. The truth likely lies in the messy middle. Warp research isn't a straight line, it's a branching maze where every dead end teaches us something new. What's undeniable is the accelerating pace of discovery. Each year peels back another layer of spacetime secrets, inching us closer to answering the ultimate question. Are we galaxies away from warp travel, or just one brilliant insight? For all the thrilling possibilities warp drives present, there's a formidable camp of physicists who argue they'll forever remain trapped in the realm of equations. Their skepticism isn't about dismissing creativity, it's rooted in the universe's stubborn refusal to bend to our wishes. Take the infamous exotic matter problem. While the math permits negative energy, no one's ever observed it in quantities beyond quantum flickers. Critics point out that hoping for an exotic matter windfall is like banking on unicorn tears to power your car. Poetic but hardly practical. Then there's the causality conundrum. Even if we somehow engineer a warp bubble, general relativity suggests it could create closed time-like curves, loops where cause and effect crumble. The universe tends to slap down paradoxes with ruthless efficiency, often through mechanisms like quantum instabilities or shockwaves. Some theorists, like astrophysicist Ethan Siegel, argue that if warp drives were possible, nature would have already evolved civilizations using them. The cosmic silence, he says, speaks volumes. Energy demands also loom large. Even with optimized models, the fuel requirements dwarf anything humanity has ever harnessed. Skeptics compare it to building a highway across the Pacific, only to realize you've drained every oil field on Earth just to pave the first mile. And let's not forget the lurking existential threats: radiation surges, space-time ruptures, or the horrifying prospect of a warp bubble collapsing into a singularity mid-journey. But perhaps the most sobering critique isn't technical, it's philosophical. Some argue that obsessing over warp drives distracts from more achievable interstellar solutions like generational ships or AI probes. The late Stephen Hawking once quipped that waiting for warp technology might leave humanity all dressed up with nowhere to go, as ecological or societal crises close our window to the stars. Yet even skeptics admit their doubts aren't final verdicts, just caution signs. Science advances by testing boundaries, and warp theory, for all its hurdles, keeps pushing us to ask better questions. Whether it's a dead end or a detour, the journey itself is reshaping how we see the universe's rulebook, and sometimes that's the real breakthrough. After this deep dive into the science, challenges, and dreams of warp drive technology, here's where we stand. The math suggests bending space to outpace light isn't impossible, just staggeringly difficult. We've slashed the energy needs from planetary scales to something almost imaginable, found quantum hints of exotic matter in lab experiments, and even glimpsed microscopic spacetime distortions. But let's be clear, we're still centuries from parking a warp-capable ship in your driveway. The hurdles can't be overstated: stabilizing warp bubbles, sourcing negative energy, dodging causality violations, each one an Everest-sized challenge. Yet history's full of breakthroughs that once seemed equally outlandish. Flight, moon landings, quantum computing, all were impossible until they weren't. Warp drives might follow that same arc, or they might remain a beautiful dead end, pushing us towards slower but steady alternatives like generation ships or light sails. What's undeniable is how this quest reshapes our perspective. Whether we crack warp technology or not, the pursuit forces us to rethink spacetime's rules, confront our cosmic solitude, and grapple with humanity's place in the universe. That's the real gift of this wild idea: it keeps us reaching. So where do you stand? Will we ever outsmart light's speed limit, or are we destined to respect its cosmic stop sign? Drop your thoughts below. Let's keep the conversation bending toward the